All right, friends, we are here and we are looking at question 10.9.22 in the Collaborative Statistics textbook. And we are checking cholesterol levels. All right, so we just talked about the danger of Likert scale data up here in 10.9.21. I got no problem with this data down here, assuming it was collected properly, because it's actually a measurement. We got a cholesterol level at the beginning, a cholesterol level at the end. Those are measured milligrams per deciliter, I believe, is how they're measured. There's some kind of a unit that is measurable by some kind of precise measuring instrument. So I'm happy with that. And we're trying to see if cholesterol levels were lowered after 12 weeks. So here's the cholesterol levels at the beginning of a 12-week study and at the end. So this is a perfect matched pair kind of test. So I say let's get in here and let's start crunching some numbers and seeing. So the first thing I'm going to do is I'm going to look at the data. Let's get in here to edit it, clear out some lists. All right, so we got 140, 220, 110, 240, 200, 180. I'm assuming we're talking about bad cholesterol too, since we're trying to lower it. I'm guessing this is LDL cholesterol. Otherwise, we want to be raising this bad boy, wouldn't we? Okay, over to L2, the ending cholesterol levels. 230, 120, 220, 190, 150, 200, 300, and last but not. Okay, we're matched up here. Beautiful. Now, we've had this discussion in class. One way, I don't think it's the best way, to look at this is to do a confidence interval around L1 and a confidence interval around L2 and see if there's overlap. That's bad for a couple of reasons. One of the reasons we discussed was that you lower your confidence to 90% from 95, because every time you add another confidence interval, you multiply by that 95%. It's the old binomial. You know, when something's 95% likely, two of those things are then 95 squared percent likely to happen. So that's one problem. The other problem is a little more mischievous. If you do it that way, you lose the interaction between the person starting and ending level. I mean, you're actually interested in whether cholesterol is reduced per individual on average. So if you don't match up the starting and the ending levels in some way, you're going to lose that bit of important characteristics. So we're going to turn this back on. And what we'll dealt with this in class is we go up to L3 and we do L1 minus L2. We'll also do L2 minus L1 if you want to, but we'll do it this way first, and we're going to strike enter. And now you see the average differences in cholesterol level. If they're positive, that means that the cholesterol at the beginning of the study was higher than at the end. If it's negative, converse. And if it's 0, that means that it's the same, 140, 140. We now have a single data set, which is exactly what we should have, a single data set. So we're going to do a little analysis of this first. I'm going to look at the data to make sure. I want to see what it looks like. Let's see what it looks like. Let's see. My data is actually in L3 with a frequency of 1. Right? Okay, and then also up here, a little box plot. Let's take a look and see if I have any outlier data that might be screwing with my averages. Okay, here we go. Let's do a little zoom 9. All right, looks good so far. Let's clean the window up a little bit. It's saying negative 20 is the lowest result. Let's increment it by 10 and see if we can maybe drop the box. That's good. I like this. I'm also going to clean up the Y scale. Why the Y scale does that, I have no idea. We'll increment that by 1. Maybe have this go to 5. Get ourselves some nice tick marks on there. There we go. So we got some negatives down here. We got some positives down here. Okay. Now, more positive results would definitely indicate that the cholesterol lowering regimen is working, clearly. Because if they're positive results, that means they were bigger at the beginning than they were at the end. So you got this data right here looking very, very nice. This is not technically an outlier. This guy out here who is, let me go see who that is. That is the one that was a 60, I think. Can we find that in our data sheet? Oh yeah, right here, the 360 to 300, the big drop. That's not being considered an outlier. It is definitely a large value. It's getting close to outlier status if you look at the IQRs here. If you look at the IQR, multiply it by 50%, he definitely is within that range, but that is pulling the average up, but not unusually so. Not unusually so, therefore not atypically so, therefore we leave it in. So our hypotheses are going to be, the null is that nothing changed. The cholesterols have stayed exactly the same on average. The research hypothesis, HA, is going to be that the average difference is positive, greater than 0, because we want to see that. If it's greater than 0, that means the starting cholesterol numbers are larger than the ending ones on average. That's going to be our set of hypotheses. Oops, let me get where's my mouse? There it is. Let's go over to test. It's just a t-test. That's all it is. We got data for sure. It's in L3 with a frequency of 1. Whoops, where did I go? L3 with a frequency of 1. And we're testing against a hypothesis of value of 0 for no change. And we want to see if it's actually gone up from 0, meaning a positive change. Let's take a look. All right, well, there's our, let me make this a little clearer for you guys too. Let me turn these plots off. If I hit graph, will I get it back? No, I have to run the test again. Sorry about that, guys. I often forget to turn my plots off before I get results. There we go. Oops, nope, there we don't go. We have to do tests, t-test, all the way down to the bottom, draw. Beautiful. Okay, so we're 1.17 standard deviations above average. Here's 0, literally and symbolically. So we are 1.17 standard deviations above. Unfortunately, that's not far enough away, as we can tell from our p-value of about 13.5%, to think that we are truly above 0. So even though on average, we had an average increase, which means an average, let's actually get that average. Let's do t-test, calculate versus draw to get the results. There they are. On average, we had a 9-point decrease. I know it's positive 9. That means on average they were 9 points higher before than after. Because of the variation, we weren't able to escape the 95% confidence interval centered around 0. So therefore, we can't believe that the cholesterol was lowered enough to be a significant lowering. Okay? But all hope is not lost. You got a sample size of 10. Right? You got a sample size of 10. So if you have a sample size of 10, if you truly believe it's being lowered, go out and get some more data. Right? Go out and get some more data. Let's just drive the point home. If you truly believe, right? If you truly believe that this is indicative of what's actually going to happen in the general population, watch this. I'm going to put 2s in. Oops, not there. You don't want that one. I'm going to put 2s in. And let's say essentially what we did was we did the study twice and we saw the exact same results 2 times. And now I'm going to rerun that t-test. But I'm going to change the frequency to list 4, which will give us 20 data points. Okay, you ready? Now your p-value went down. It's still not below 5%, but it's more significant. Because even though you got the exact same results and therefore the exact same statistics, let's get the calculate for you, the exact same statistics, because you have a larger sample, the standard deviation is exactly the same as well, but the standard error, which is the inferential measure, is going to be shrunken by a factor of √2, and that's why it became more significant. So my suggestion to you guys is, if you get data that is not is A, not significant, but B, you think there is significance there hidden somewhere, go replicate the study or go find a study that has similar results and see. Maybe it does. All right. I hope that helped, and we'll catch you in class.